All right, and like I said, we're going to continue. All right, so next thing is to actually figure out how to write out the equation for our different precipitation reactions. A molecular equation and an ionic equation are our next two topics. The term molecular means that we are listing our reactants and products all as they were given. This is like an actual chemical equation. You've seen these before. From here, we can talk about an ionic equation. In order to write out an ionic equation, what we're going to do is we're going to take that molecular equation and we're going to break it up into its individual ions. We're going to write out some rules. You're going to break the ionic compounds down first into cation and anion. And then you're going to leave solids, liquids, and gases alone. Do not break these up. Okay? So first step is to break the compounds into cation and anion. The next is to leave the solids, liquids, and gases alone. The last step, and I'm sorry I'm going to write it kind of weird, but the last step is to cross off species on both sides of the equation. So in other words, common ions after you've broken it apart. And I'm sorry my handwriting is atrocious. It's unintentional. But that being said, once we cross off both sides, then we're going to, step 4, rewrite what's left. As far as the equation, this is going to be then referred to as a net ionic. Okay, so pause your video and write these steps down. We're going to do this one together. The next slide has already broken them apart. So after you're done writing these down, go ahead and play the video again. I'm going to erase all of this so I have some space. Actually, you know what? I think I'm going to leave it and try to start down here. All right, so first thing I'm going to do is I'm going to break this one apart. It is aqueous, which means ionic. So I'm going to break it into its individual parts. I know that since nitrate is a +1, that Ag must be a +1. And I know nitrate is a -1. Sorry. Same thing for this one. Since it's aqueous, it's also going to get broken down into its individual parts. I know that K is a +1 because of its location, and because chloride is a -1 because of its location. That's all on the left side of the equation. On the right side of the equation, I'm not going to touch the solid species. And remember, if you go back to your solubility rules, AgCl is one of the ones that is going to be insoluble. Remember, it's one of the exceptions to the solubility rule. Remember, all chlorides are supposed to be soluble, but it says that silver 1 is an exception, which makes it insoluble, which is why we've written it out as a solid here. The next thing is going to be the KNO3, which is aqueous, which means it needs to get broken apart. Okay. From here, step 3 is to cross anything on both sides off. And so we're going to move on to our next slide for that. We're going to see that we've got everything broken down like we've seen before. And from here, what we're going to do is we're going to cross off the ones that are on both sides. So we've got NO3 on both sides, and we've got potassium plus on both sides. Cross them both off. What's left is going to be our net ionic equation. So our last step is to rewrite it. We've got Ag plus Cl minus on the left, and then we've got AgClS on the right. And so rewriting this equation leaves behind our net ionic equation. Okay, we are going to practice with this in the next few days. We're going to see some practice problems. We're going to see some problems that we should work on in our homework and things of that nature. Please don't freak out if you're still kind of worried about it. I'm going to go through and do a couple of practice problem videos for you to look at tomorrow to accompany the homework set that you have to work on. So just so you know, that being said, anything we crossed off has a definition. It's called a spectator ion. It's something watching what's happening but does not participate in the final product. Okay? All right, next thing is just going to be get your steps written down. Look, we already did that. Dissociate anything you need to. cross out anything that remains, and then rewrite the net ionic equation, okay? So there is a steps video if you want to pause and you want to rewrite these ones instead because you can see them better. I apologize if they're out of order. This should have come before the actual problem. I'll have to remember to move that. All right, next is going to be, and this is our last topic of this chapter, acids and bases in gas chemistry. So remember, we have very basic definitions of acids and bases in our brains. One thing that comes to mind when you think acid is probably, oh yeah, they dissolve things, blah, blah, blah. Okay, great. Well, acids and bases are a little more complicated than caustic chemicals that cause burns, all right? They are very, very useful. We use a lot of acid-base chemistry in our bodies, in the different enzymatic processes and metabolic processes that maintain our bodies. And so these are kind of important for us to learn a little bit of the chemistry about. Up here we have our first definition, and there's several definitions. I will make sure to highlight what those definitions are so that you know what I'm looking for. The Bronsted-Lowry definition is our most common and, to me, most useful for learning chemists. The Bronsted-Lowry definition is the one that I will make sure you know whether you like it or not. The Arrhenius definition was just, these go from what we would call more general to more specific. The Arrhenius definition is a very general definition of an acid or a base, which says, for acids specifically, that as substances are dissolved, they increase the concentration of protons, H+, when they are dissolved in water. So an acid is just defined as something that increases H+ concentration. The Bronsted-Lowry definition, which is a brilliant definition in my opinion, takes acids and calls them proton donors, okay? Of course, the last definition that we are going to work with is called the Lewis definition. I don't believe that we talk about that one much in this chapter. We might just mention like the definition of a Lewis acid and a base. But for now, just understand that I'm holding you to understanding what these two are. This one I need you to know. This one I need you to actually deep delve and understand in a big way. So we'll look at the 7 strong acids. We already talked about these. Please make sure you memorize them. I need you to know if I write hypochloric acid or perchloric acid, what it is. I need you to know when I write nitric acid, what that formula is, because you're going to be given word equations and asked to write them out. Now, that being said, then we flip over to the other type of definition. Arrhenius' very general definition of bases says that when dissolved, they increase the concentration of the hydroxide ion when dissolved in water. And a lot of acid-base chemistry, if not all acid-base chemistry, is done in water for a reason. We'll talk about why in the future. Bronsted-Lowry is going to be referred to as a proton acceptor. So you can see that the Bronsted-Lowry definition is actually very useful because it sticks to one species, protons. Remember that a proton is an H+ ion? And Bronsted-Lowry says that an acid is going to be a proton donor and that a base is going to be a proton acceptor. So pretty easy to track as long as you have protons in your solutions. The strong bases are going to be hydroxides, like we talked about, the group 1 metals, and then the group 2 metals, calcium, strontium, and barium only, all connected with an OH- ion. Okay? From here, we talk about the term acid-base reaction, also known as a neutralization reaction, which is one you read about. In the acid-base reaction, the acid is going to donate a proton. Again, why I wanted you to know. Water can be both an acid and a base. We refer to it as amphoteric as a result. In this particular case, water is acting as the acid, donating one of its hydrogen ions, or its protons, to NH3, the base in this particular case, because it is the thing that accepts the proton. Okay? When acid and base are combined, typically the two products are liquid water. This is a typical thing, right? We're not going to say all acid bases result in these, but in general, we end up with something aqueous or ionic, if you will, and we end up with liquid water. So this is a type, if you will, of solution chemistry that involves, if I wanted to write a net ionic equation, I would break up this, I would break up this, and I would break up this, but I would leave this alone, right? Because only solids, liquids, and gases stay together in that solubility equation. So if I wanted to get a net ionic equation, which is of course where we're going with this, then I would break everything up and I'd cross off what's on both sides, just like we saw our steps before. and then I would get what the overall net ionic equation is. So here we're actually doing that process. Most neutralization reactions have the exact same net ionic equation. This is a basic acid-base reaction. Strong acid, strong base, right? Strong acid, strong base reaction that results in a salt and water. Okay? These are going to be very common. This net ionic is the common one when we talk about strong acids and bases, even when we talk about weak acids and bases. Okay? From there, the last type of solution-oriented reaction we have to discuss is going to be a gas-forming reaction. These gas-forming reactions are similar to what we've seen in the past in that something is going to react together to form things, but in the case of a gas-forming reaction, one of the products must be a gas. In this case, we have another example where we've got a gas being formed. You'll notice that one of the things that comes along with a gas is a liquid being formed, in this case water. The most common types of gas-forming reactions are going to be ones that are discussed. I do not care that you know these reactions. I care that you pay attention to the chemistry that's happening. In other words, that a solid is being added to something and that a gas is formed. So if I gave you this reaction, I would ask you, what do you know about this reaction? One thing you could tell me is it's a gas-forming reaction because a gas is formed. Make sense? I'm not asking you to memorize these. I'm not asking you to do anything with them right now. All I'm asking you to do is be able to identify when a gas is being formed. Now, in this case, you could do a net ionic equation. If we wanted to do it, we would split it up. Now, when we do net ionic equations, if you have subscripts, those have to go out in front unless they are polyatomic ions, which of course you do not break up. I've got H plus. This is an aqueous compound, so I'm going to put 2Na plus and SO4 2 minus on the right. And we're going to leave H2S alone because it's the gas. So if I want to, next thing I can do is I can cross off what's on both sides. I've got sulfate and sodium. That leaves behind S2 minus, not plus 2H plus makes H2S gas, which makes total sense if you think about it, because those are the two things that are involved in that particular gas formation, okay? So that being said, we're going to stop there. We're going to talk about oxidation reduction reactions in the future. For now, that's all, folks. You'll see a practice problem video tomorrow, but I would like you to get started on those chapter 4 sections 1 through 3. It's like the homework that I posted. Just see what you can answer without me, and then tomorrow we'll do some practice problems via video, just like